Hello everybody, in this video I will show you how to use your graphing calculator to solve problems with binomial distribution. Okay, let's see what we have here. The probability of a plant surviving in Kendall's garden is 0.7 or 70% chance. And if she plants 24 new plants this year, calculate the following probabilities rounding your answer to 4 decimal places. Now before we start doing our computations, we need to make sure that all conditions for the binomial distribution are satisfied. First, let's see, we need a fixed number of trials. We have 24 new plants that need to be planted this year. This is your number of trials, and the notation for this is n. Okay, so this is 24 plants. Then we have 2 possible outcomes for each trial. In our case, we're going to say that success if the plant survives. So success is the plant survives. Okay. Otherwise, it's failure. Okay. Then the probability of success is the same for each trial. So the probability in our case is 0.70. And the trials are independent, so whether one plant survives or doesn't, that should not affect what happens to the other plants. And the random variable x represents the number of successes that occur. So in our case, we can get anywhere between 0 and 24. That's the values of our random variable. Okay, so the first problem says, what is the probability that exactly 20 plants survive? What does that mean? How will we write this? So probability that our random variable x takes a value of 20. Okay. Now, when we find probabilities of our variable taking one particular value, we will be using a command that's called binomial PDF. And then we have to follow some syntax associated with this command. So let's go ahead and use your calculator. Where would I go? Okay, let's turn this on. We go to second variables, second vars or distribution, and then we're going to scroll and find the command that says binomial PDF. Okay. We select this, and the syntax goes as follows. The first, you need to tell how many trials there are in this experiment. So 24 in our case, comma. And then the probability of success for each individual trial is 0.7. And how many successes we're interested in? Well, in our case, it's 20. Okay, so over here, let me write it, 24 trials, 0.70, that's the probability of one success, and then we're interested in exactly 20. Okay, let's press enter. So we would like to round this to 4 decimal places, right? So this is 0.687, 0.687. This is your chance of getting exactly 20 out of those 24 plants surviving. Okay, well, let's see. What is the next question asking us? The next one says, what is the probability at least 14 of them survive? Now, what does at least mean? At least does not mean just 14. It means 14 or 15 or 16 and so forth. So this is 14 or more, right? 14 or more plants survive. Okay, so how would I do this? So this is probability that random variable takes the value of 14 or more. Okay, now one way for you to do this is compute the probability of getting 14, 15, 16, 17 and so forth all the way to 24 plants and add them all up. But this is very long and it's not needed. So what we need to do here, we need to use a complement. Okay, the complement of this would be probability that we get less than 14, right? and I'll explain why we use the complement here, less than 14, and we need to subtract that probability from 1. Now, why do we do this? Probability that less than 14, we can compute that on a calculator, 1 minus binomial CDF. And why is it computing it this way? Because your calculator is going to compute probabilities up to a certain value, starting from 0 and up to the value that you provide. Okay, so when I write it like this, 24.7 and 13 goes over here, this probability will be the summation of all probabilities of successes, 0, 1, 2, 3, all the way to 13. And that's how your calculator is programmed. It's going to sum the probabilities of events where you have 0 through 13 successes. Okay? Your calculator cannot compute from, let's say, 14 up to 24. It can only do from 0 to a certain value. So that's why we have to use the complement here. Okay, so again, this binomial CDF, now make sure that we use C, not P, CDF, this command will compute and add at the same time all of the probabilities of events where you have anywhere between 0 and 13 successes. Okay, so how would I put that in the calculator? Just like that. So I would do 1 minus second distributions, and I'm going to go ahead and find my command binomial CDF here. Okay, 24 trials total. The probability of success is 0.7 up to 13, right? Okay, just like this, and then we get 0.9257. Well, 58, right? So 9258. Okay, that's a pretty high chance. Yes, so this is how you would compute the probability of an event where you have at least 14 successes. Okay, all right, let's take a look at the next one. At most 10 of them survive. What does at most mean? What does at most? Okay, at most means 0 plants survive, 1, 2, all the way to 10, right? This means no more than 10. No more than 10. Okay, so how would we do this? Now, here, this means the probability x is less than or equal to 10. Okay, if you take a look at the problem above, this one greater than or equal to 14. This one is less than or equal to 10. Now here we're also going to use binomial CDF, but now in this case we do not need to do the complement rule because your calculator will compute all of these probabilities, 0, 1, 2, 3, and so forth, all the way to 10, and add them in all in one command. So we need to do binomial CDF, okay, 24 trials, probability of success is 0.7, and we're interested up to 10 successes. Okay, so that's what you would plug in your calculator. So we'll go to second distribution, binomial CDF, 24, comma, 0.7, comma, 10. Okay, at most 10. All right, so we get 0, 0, 36, 0, 0, 36. That is your probability of getting at most 10 plants surviving in the garden. Okay, let's do this one. Exactly half. Well, this one is easy. This is probability. X is exactly half, which is 12. Okay, again, whenever you have equality here, not inequality, then we use binomial PDF. Binomial PDF. 24 plants, probability of 1 success is 0.7, and we're interested in 12 successes. Okay, let's see what we get. So second distribution, 24 comma 0.7 comma 12 plants. Okay, and 0.199. Okay, so let's call it 0.02. 0.02. All right. Okay, let's see the next one. This one is similar to one of the problems that we've done. No more than 3 of them survive. Okay, no more than 3 of them survive. That means 0 survive, 1 survives, 2 survives, or 3 survives. If you think about it, this probability should be relatively small because the probability of 1 success is 0.7. So if only 3 of them survive, that's very unlikely to happen. So you should expect a relatively small number. So let's see what happens here. No more than 3. So probability that x is less than or equal to 3, right? That's what no more than 3 means. Again, here we will be using binomial CDF. Binomial CDF. Okay, 24 plants planted. 0.7 is the probability of success, and when 0 and 3 survive, let's see what we get. Okay, second distributions, 24 comma 0.7 and up to 3, right? So we should expect a relatively small number. Okay, when you get a number like this, what does this mean? So you have 7.7 times e to the negative 9. This is actually scientific notation. What it really means is 7.7 times 10 to the negative 9. So let's say this is 7.7 times 10 to the negative 9, which means there are 8 zeros in front of the 7. Okay, so this is approximately 0.0000. All these zeros, let's see, what is it for? 77. Okay, let's go ahead and call it a 0. Okay, basically saying it's very unlikely that only 3 or less plants will survive. So your intuition was right when you thought, okay, this is unlikely to happen. The probability of this event should be very small. Okay, let's see. What is the last problem asking us to do? She has a good year and all of them survive. What does that mean? Okay, so this is probability that all plants survive. So this is x is equal to 24, right? Okay, this is binomial PDF. Okay, we're interested in exact number of successes. So 24.7, 24. Let's see what we get. Second distribution. Okay, PDF here, 24 plants, and probability of success is 0.7, and we got 24. If you think about this one just for a minute, it's probably unlikely that all of them will survive, right? If the chance of one of them is surviving is 0.7, so let's see what we get. Okay, so this one says 1.9 times 10 to the negative 4, right? So 1.9 times 10 to the negative 4, so that's about, let's see, 0.00019. That's still pretty small, so let's go ahead and call it also 0. Very unlikely to happen. Okay, so this is it. This is how you would solve your binomial distribution problem, where you have a finite number of trials. Probability of success doesn't change, and the trials are independent of each other. Okay, thank you for watching.